Hello everyone, welcome to GATE Pass. In this video we are going to start the problems that appeared in GATE 2017 and that were related to thermodynamics. So these were the two problems, question number 6 and 7, which appeared for 1 mark, and there was a negative marking of 1/3 mark for each of them if you get it wrong. Okay, so these are very simple problem. Let's quickly go through them. So the first problem, it gives you that you have two gases M and N, their operating pressure and temperature are given in this table. So for M the operating pressure is 25 bar and temperature of 300 Kelvin. For N the operating pressure is 75 bar and temperature is 1000 Kelvin. Okay. Now they have further given that their critical pressure and critical temperature are as follows, which are given in the table. Fine. Now they have said that the volumetric properties of these gases, they are described by the generalized compressibility chart. Okay, so what it gives is that it gives Z as a function of reduced temperature and reduced pressure. Those are your generalized compressibility charts. Okay, now they have said that at given condition, what is the relation between the compressibility factor of gas M and gas N? Okay, so this is a very straightforward problem and it is based on your two parameter corresponding state theorem. Okay, what does your two parameter corresponding state theorem states? It says that when you have two gases which are at same reduced temperature and pressure, okay, then they deviate to the same extent from the ideal behavior. What does that mean? That means that both of them have same compressibility factors. So first of all, let's calculate your reduced pressure and reduced temperature for these gases, and what you get is that for M your reduced pressure is 25 by 75, that is 1 by 3. For N it is 75 by 225, it is again 1 by 3. Okay, what is your reduced temperature? For M it is 300 by 150, so it is 2. For N it is 1000 divided by 500, that is again 2. So what you see over here is that these gases, they are at the same reduced pressure and same reduced temperature. So according to two parameter corresponding state theorem, then they should deviate from ideal behavior to the same extent. That means that their compressibility factors should be same. So Zm equal to Zn. So it was a very simple problem. Next, let's see question number 7. In this case, what they tell you is that you have water at 40 degrees centigrade. You want to heat it to 80 degrees centigrade. It is done in two processes. In first process, what they are doing is that they are bringing water which is at 40 degrees centigrade in contact with the source, heat source, which is at 80 degrees centigrade. Okay. In the second process, what they are doing is that they are bringing the water at 40 degrees centigrade in contact with the source which is at 60 degrees centigrade. Once the temperature rises to 60, then they bring this water in contact with another source which is now maintained at 80 degrees centigrade. Okay. And now they have asked you, for these two processes, identify the correct statement. Okay, so let's see one by one what are the statements. Okay, statement A says enthalpy change in process 1 is greater than process 2, or enthalpy change in process 2 is greater than process 1. Let's see what is happening to water. Water is going from 40 degrees centigrade to 80 degrees centigrade. Okay, in the second case also the water is going from the final state, from initial state of 40 to the final state of 80 degrees centigrade. Okay, now so the thing is that the final state is same. Since enthalpy is a state property, so if the final states are same, then the enthalpy change should also be same. Okay, so in this case your statement A and statement B are wrong. Now let's see statement C. It says process 1 is close to reversibility, and D statement says process 2 is close to reversibility. Let's first of all understand that heat transfer, when it takes place through a differential change in temperature, let's say dT. Okay, now this process, it will be said reversible only when this dT tends to 0. Okay, now you all know that heat transfer cannot take place unless and until there is some difference in temperature, because heat flows from higher temperature to lower temperature. So that's why you cannot have a reversible heat transfer, okay, in any process. But that process can be close to reversibility or far from reversibility depending upon what is the value of delta T. Okay, so if the heat transfer is taking place through a small difference in temperature, then that process is more closer to reversibility as compared to the process which is taking place when the temperature difference is large. Okay, so in this case, let's see what is the temperature difference. Your delta T for process 1 is 40 degrees centigrade. In process 2, the heat transfer is always taking place when delta T is equal to 20 degrees centigrade. So since the differential change in temperature is less in process 2, see over here 60-40, so delta T is 20, 80-60, so delta T is 20. So in that case we can say that process 2 is close to reversibility as compared to process 1. Okay, so this statement is wrong and this statement is right. So let's now move on to another problem. So this is question number 33, which appeared in GATE 2017 for 2 marks. Okay, so it gives you that there is a sparingly soluble gas in equilibrium with solvent. When you see that it is a sparingly soluble gas, okay, immediately you should remember that now, because we are talking about that mole fraction approaching to 0, so you have to apply your Henry's law. Okay, now the pressure is given as 10 bar. The mole fraction of solvent in the vapor phase is given as 0.01. From that we have calculated the mole fraction of the solute, that is of the gas in your vapor phase. So basically your gas is now your solute, okay, because it is dissolving in some solvent, right? Further they have given you that its fugacity coefficient in the vapor phase is 0.92, Henry's constant is 1000 bar. They have asked you to calculate what is the mole fraction of the solute in the liquid phase. Okay, so let's first write down our Henry's law. Okay, now they have given you the fugacity coefficient in the vapor phase. That means that your vapor phase is not behaving ideally, but they have told you that liquid phase obeys Henry's law. That means they have told you that your liquid phase behaves as an ideal solution, but your gas phase, it deviates from ideal behavior, and for that they have given you a fugacity coefficient phi. Now let's say that my solvent is component A and my solute is component B. Okay, so then I can write phi B multiplied it with YB and pressure, that is equal to XB into Henry's constant. Okay, so now this is your modified Henry's law. Okay, now you have to simply plug in all the values and find out what will be the value of X solute, which is nothing but your XB. Okay, so that's what I am going to write. Fine. So phi B is 0.92 multiplied with YB, that is 0.99. Your total pressure is 10 bar, that is equal to XT, which you want to calculate, into Henry's constant, that is 1000. So your mole fraction, that is equal to 9.108 into 10 raised to minus 3. Now in the question, if you write this, it will be wrong, because in the question they have specified that you have to write down what is the mole percentage of the solute in the liquid phase. So if you want to calculate the mole percentage, multiply it with 100. So you get an answer as 0.9108. Okay, so this is your answer. Further they say that round it off to 2 decimal places, then you should just write 0.91. So make sure in what terms they are asking you your final answer. So I hope you understood the problems. They were easy. Remaining 2 problems we will take in the next video. So thanks for watching, and please don't forget to subscribe to my channel and like this video. Thanks a lot for watching.